Okay, so this video is meant to fill in some of the gaps on the electric generator. Um, so let's go ahead and quickly talk about some of the features that kind of weren't covered on the previous video. So here's what we have. We have a magnetic field that's uniform, and here's a current loop, or sorry, a wire loop. In fact, probably a number of wire loops that are all oriented to catch flux. And then what we're going to do is we're going to rotate by external means. We're going to supply a rotation. So the rotation is the input. There's some angular speed that goes in, and the induced current from Lenz's and Faraday's law is going to be what we get out. So essentially, rotation is the input and current is the output. That's the idea of an electric generator. So let me remind you how you compute flux. Flux, if you have the magnetic field is constant across the entire area, then you can just do the B dot A, and then if you have a number of loops catching it, so this isn't just one term but a bunch of them, then we can multiply by the number we have to get the total flux caught. So B dot A is BA cosine theta, where theta is the angle between the magnetic field and the normal vector. So it's what we use, it's the basis of our flux calculation. This is the angle between B and basically the area vector. Remember, the area vector gets its direction from the normal vector. So the area vector is just the area of the loop and coupled with the normal vector. So we can go ahead and recognize that that angle theta will change because of this rotation, and so theta equals omega times t. So that's basically just distance equals rate times time, angular version. I would certainly recommend that you stay in SI units here, so let me put it down here. Theta equals omega times t. So angular speed, I would take it in radians per second and then multiply by seconds, and then of course the seconds will cancel and you'll wind up with radians. And so that angle change, of course, is the heart of why we get any flux change in the first place. And so when we put theta equals omega times t in there, we get this function of time. Our flux changes as the cosine of the angle, and the angle changes as a function of time. Now, of course, this does assume, looking at this equation, that at t equals 0, theta is 0, so my clock does start in this orientation. When t equals 0, theta is 0. If you don't like that, if you don't like your clock starting at this particular position, you can use what's called a phase angle here. And if you have gone far enough in talking about simple harmonic motion in Physics 1, or you've in Physics 3 talking about waves, and you know what I'm talking about. If not, then ignore it completely. There's no harm here in starting our clock in a particular orientation. That's not the interesting part, really. What's interesting is what happens over time. So what happens over time is that this loop is rotated, so the normal will rotate with it, and we can kind of do the play-by-play here of what happens in one full cycle of rotation that just happens to start with the time here. And before I even get to that, I should mention, of course, that you would really want to make sure to stay in SI units here, radians per second for the angular speed and radians for the angle. It doesn't really so much harm you if it's contained completely inside a cosine function, because of course then you just put your calculator into whatever mode. If you're working in degrees, then you can just you could work in degrees per second in degrees, because if you tell your calculator that you're working in degrees, when you take the cosine of it, it'll all get sorted out. However, down here, as you'll see, some of that stuff will start to be naked out here, not inside a trig function, and then it's really important that it is in SI units. So I would recommend just doing that in the first place. So omega radians per second, not revolutions per second, not revolutions per minute, not degrees per second, radians per second is SI, and then over here the angle is in radians. Not degrees, not revolutions, radians. Okay, so if we go ahead and we put that in, theta equals omega t, we get this nice equation. This is a cosine function, and I've gone ahead and drawn that nice cosine function here. The the flux will oscillate from maximum to negative maximum. That's what this says. I know it's a little hard to read. This is the plus max, this is the minus max, and it bounces back and forth between those. And of course, that maximum is set by this. So NBA is the max. And that's actually where we start. Of course, this loop is oriented to catch maximum flux right at this moment, maximum positive flux, because the normal vector points in the same direction as the magnetic field. So you can see we start off here. I tried to make these all line up. So here we start with the positive maximum. You might remember, of course, that when you're computing the flux across an open surface, there is an ambiguity in how to do flux. So you could pick the normal to point to the right or the left here. So this particular equation just kind of assumes that at t equals 0, your normal is exactly aligned with the field. It's a 0-degree angle, so you'll get the positive flux max. And then, we of course, rotate it. So this is going to rotate, and I've kind of drawn the play-by-play here. Once we've picked the normal, we want to stick with it. We don't want to change it. So that once we choose that normal, once it rotates 90 degrees, so this will be a quarter of the way through the sinusoidal cycle, so a quarter of a period. Now the angle is 90 degrees, your flux is 0, and you can see that here. Cosine of 90, of course, is 0. And then here, the normal has rotated to 180 degrees, so now the normal is exactly opposite the field. You get the negative maximum flux. And then from there, and that's halfway through, or period over half the period through the cycle. Now at this point, of course, the maximum angle between two vectors can only be 180, so that's, we've already reached the maximum angle. So at this point, technically the angle will start closing again, although it doesn't really hurt you to have that the angle goes from 180 to 360 either. All the values of the cosine will be the same. But let's just say that this rotates another quarter of a rotation. We're now at 3/4 of the way through the period. You can call that an angle 90 or 270, doesn't matter. And then when one period has passed, we're exactly back to here, and you can see we're back to the positive flux maximum. So that's how the flux varies. And of course, the flux change with time is exactly what gets us our EMF. Right here, here's our Faraday's law here with the derivative and the minus sign in the front. So this is one of the few cases where you can't really work with deltas. You do have to work with the full derivative. If you noticed in the other video, that I did a very hand-wavy derivation of this. I called it magic because, of course, those students don't have calculus. But here, this is one of the few times where we can just take the derivative here. And I am going to keep the minus sign in the front, even though I would normally just chop it and ignore it. In this case, I'll keep it just because it'll wipe out with another negative sign in a moment, and that will just kind of save me the trouble of just chopping them both, because they'll kill each other. So I take the derivative of the flux formula with time. That's a cosine, so derivative of cosine is minus sine. And then, of course, you got to take derivative of what's inside. So the derivative of what's inside with respect to time is just omega. So here I have, there's your minus sign, and then I pull out the derivative of what's inside. So that's omega. And then you can see that this minus sign and this minus sign wipe each other out. And I wind up with this equation, which is a sine function. And there's the sine function, which I kind of just characterize as, okay, it sloshes back and forth. And the other one, that's really all I had mentioned in the other video, but here we're doing a little bit more of a play-by-play. So this is a sine function. I've gone ahead and drawn it as a sine function. And of course, the plus max and minus max are set by whatever is multiplied in the front. So in this case, the maximum EMF is set by NBA omega. So this, I'll write it down here again. The maximum EMF is set by this quantity. I talk about why that makes sense in the other video, and then of course, as goes the EMF, so goes the current. So that's just from Ohm's law. So they just differ by a constant factor. So if this goes as sine, this will go as sine. So the current function looks very similar. So we do get that sloshing back and forth current, which we call AC, or alternating current. So that's all covered in the other video, but what I wanted to show you here was a little bit of a play-by-play of the flux versus the EMF. And I wanted to point out something. At this moment, when you have the positive maximum flux, you actually have zero EMF. And so that might seem counterintuitive, but remember that it's not the flux that gets you EMF, it's the change in flux, right? It's all about changing flux. So even though the flux here is maximum, I will point out, when you have the flux that's maximum, you just finished growing up to that maximum value, and you're just about to go back down from that again. Of course, when you're at the maximum, there's only one way to go, right? So you've come up to it, and you're just about to go down. And so what I want to point out is that the slope is zero. So its rate of change is zero, so of course that's what the EMF is tied to. So even though the flux itself is maximum, because the slope is zero, the EMF is zero. Now, conversely over here, you look at this, well, at this moment, there is no flux. The normal vector is 90 degrees to the field. However, I want to point out that its rate of change is actually the largest there, and that is why you have the largest EMF there. So again, remember that the EMF is tied to the rate of change of the flux. So if you want to know what the EMF is going to do, you need to look at not the value of this graph, the flux graph, but the slope. So just to kind of reiterate, over here, we reached the negative maximum flux. Again, that might be the maximum flux, but its rate of change is zero, and therefore the EMF is zero. And then over here, when we again reach the state of zero flux, it actually has its greatest rate of change, so that's why the EMF is maximum. So there are a couple homework questions there that sort of ask you to tie in the play-by-play of, well, when the flux is maximum, or when the EMF is maximum, when the current's maximum or minimum, what is actually going on with the loop at that time. So hopefully that little bit play-by-play helps you a little bit with that.